Modern athletic wear behaves differently from the heavy garments people wore a century ago. Today's gear dries in minutes, stretches under tension without tearing, and weighs almost nothing. That performance gap exists because we stopped relying exclusively on nature for materials. We started wearing nylon. This comparison shows why natural fibers struggled to keep up. Cotton acts like a sponge, retaining massive amounts of water. Wool provides warmth but adds significant bulk and weight. And silk, while smooth, is notoriously fragile under stress. Scaling these fibers for a growing population required massive tracts of land for crops and millions of sheep for wool. By the early 20th century, textile production hit a hard biological ceiling. As global demand for clothing exploded, industries searched for an artificial alternative, a fiber that could be manufactured in a chemical plant rather than harvested from a field. Humanity had reached a point where biological agriculture could no longer meet the physical demands of modern life. We had to begin engineering thread from the molecule up. In the 1930s, a research team at DuPont, led by a chemist named Wallace Carothers, began exploring how to build entirely new materials. Their goal was highly experimental, synthesizing new molecular chains from petroleum-based chemicals. They eventually developed a fiber with no biological ancestor. It was lightweight, smooth, and stronger than any natural equivalent. They called it nylon. This cross-section reveals its first advantage: hydrophobicity. A porous cotton fiber acts like a sponge, but dense nylon repels water droplets entirely. At the molecular level, tightly aligned polymer chains give nylon exceptional tensile strength, resisting breakage even under extreme pulling forces. Consumers had never seen a material that combined this level of elasticity with such durability. When it debuted as women's stockings in 1940, stores were swarmed by millions of buyers within days. This was the first time humans successfully dictated a fabric's performance at the atomic level, rather than working within the limits of biology. But as World War II broke out, global silk supplies were suddenly severed. The material that made stockings popular was now needed for the war effort. Nylon became the strategic replacement for silk in parachutes. It was light, strong, and unlike natural fibers, it resisted the rot and mildew common in damp theater environments. Production ramped up to supply the military with waterproof tents, heavy-duty ropes, and specialized logistical gear that could withstand the harshest conditions on Earth. For soldiers, carrying synthetic equipment meant shaving pounds of dead weight off their packs, directly reducing fatigue and allowing for faster movement through difficult terrain. The conflict proved that synthetic textiles were reliable tools for survival, moving the material from an experimental novelty to a vital technology. After the war, this utility transitioned into civilian outdoor gear. Before nylon, camping meant wrestling with heavy, waterlogged canvas tents and bulky cotton jackets that dried slowly. As nylon replaced these burdensome materials, backpacks became stronger, and windbreakers became light enough to fold into a pocket. Mountaineers could climb higher and faster with gear that no longer absorbed the weight of the rain. Athletes adopted these synthetics because they managed moisture and body heat far better than cotton ever could. Fashion designers used the fiber's versatility to create textures, sheens, and sharp silhouettes that were physically impossible to weave using traditional looms. Modern clothing categories like moisture-wicking shirts, compression leggings, and technical shells are the direct results of this era of experimentation. In just a few decades, nylon converted basic apparel into a system of calibrated gear that actively manages heat, water, and movement. However, the same durability that makes nylon so effective also makes it a lasting environmental challenge. Those unbreakable polymer chains don't easily break down in nature. As a petroleum-based plastic, nylon requires significant energy and chemical processing to produce, contributing to a heavy carbon footprint. And the problem continues in our homes. Every time a synthetic garment is washed, friction snaps off microscopic plastic fibers. These fragments travel from our laundry machines directly into global water systems and ecosystems. This creates a direct conflict for outdoor brands that build their products on synthetic performance, while simultaneously advocating for the protection of the natural world. Today, the industry is searching for a solution through recycled nylon, bio-based alternatives, and closed-loop manufacturing systems that aim to capture and reuse waste. The invention of nylon increased our physical capabilities and expanded our reach into the wild.
For more content like this, like and subscribe to our channel.